You don't need me.
Good, good afternoon, everyone.
Are you an expert?
Welcome to today's physics colloquium.
Okay.
It is an immense pleasure and great honor that I am introducing today's colloquium speaker, Nobel laureate Reinhard Genzel. He was awarded the Nobel Prize in Physics in 1920.
Yesterday we had a
Currently,
very nice bright sky.
Okay, right. Thank you, Reinhard. Currently, Reinhard is director of MPE in Garching, the Max-Planck-Institut for Extraterrestrial Physics. He is scientific member of the Max-Planck Society. He is professor of the graduate school at Berkeley, Physics and Astronomy Department, and honorary professor at the LMU in Munich, the Ludwig Maximilian University. And a bit of history. Reinhard obtained his PhD in Bonn in 1978. And from there, and for the next 2 years, 78 to 80, he was a postdoctoral fellow at Harvard Center for Astrophysics. And then for the next 2 years, 1980 to 82, he was a Miller Fellow at Berkeley. While he was a Miller Fellow, Caltech made him an offer as an assistant professor. As soon as the news reached Berkeley, Berkeley counter-offered to him an associate professorship, which he accepted. And then 4 years later, he became full professor at Berkeley. A year later, he moved to Garching as director of MPE, where he has been now for 40 years. He retained, though, his professorship at Berkeley for many years, part-time, and currently only as a professor at the graduate school. His awards and honors cover a whole page, so I will skip them. Today, we will hear about black holes directly from the horse's mouth. Reinhard.
Thank you, Nick. You're so kind. Yeah, well, that's an unusual colloquium. We certainly didn't plan that. But the red skies yesterday were impressive, I have to say. So the subject, black holes, is, of course, very popular in so many ways. If you look at the AstroPH collections every day, you surely will see at least several discussions. What I will do today, though, is to show you the really fantastic progress with several techniques which have been possible over the last years. Now, this is not 2 years. This is even not 10 years. It turns out this is sort of 40, 50 years, and so I'll skip through some of these points so that you can see where we are now. So, of course, this really all started 110 years ago, in November 25th, 1915. Albert Einstein there presented his equations and also some derived consequences. For instance, the light deviation by a source of gravity, so that photons can see gravity as well. The imperial motion of the planet Mercury. And so that was already a good start, but the first really full solution managed Carl Schwarzschild, the guy up on top, about 6-7 months later, when he was at the front in Russia. And he actually found a solution, the full solution of the metric, which you see below, for a spherically symmetric mass distribution. And this Schwarzschild solution, in a way, is sort of both the simplest, but also the one which you, in some ways, have the easiest access to. Higher order terms like the issue of spin came later. That was Roy Kerr, the one in the blue sacco there. And then, of course, also electric charge, which turns out in the case of astrophysical big astrophysical black holes, probably are not all that relevant, because once you have a charge in interstellar space, you will have a current which will, nullify the charge. But in any case, the Schwarzschild metric has obviously two apparent singularities. One at zero, and that's truly the spectacular new discovery of Einstein's theory, that there is a singularity of space and time at exactly the point of the center of this object we call black holes. Then there is a second singularity apparently in the metric, when this quantity Rs, the Schwarzschild radius, is equal to the radius of your, say, object you are seeing going in there, or when you have a rocket going in. Now, it turns out that if you look at that solution, then there is no possible real geodetic solution for a particle with mass, or actually photons from within the Schwarzschild radius. So this 2gm over c squared is sort of the communication barrier, and that's the one which is surprising at first. And then you wonder, of course, well, how would you then see such objects, which, if you can't see photons? And so I'll tell you the story how we, over time, with the several techniques, have been encroaching ever further closer to the central objects. Now, of course, there are other people I'm sure undoubtedly know, Roger Penrose, who put this all in a very general footing, Bekenstein, Wheeler, Bardeen, and then of course Hawking, who tried to expand into the quantum part of it. Now, of course, as you probably all know, there is no currently accepted quantum theory of gravity, and that's one which actually, everyone is fighting for. And just what will happen if we have that solution is not so clear, because whilst in particle physics, of course, when you want to go at ever smaller scale, well, you have a bigger accelerator and so forth. In the case of a black hole, honestly, there's a problem, right? Because if you go inside the event horizon close to the central singularity, if it's not a point, well, then how do you communicate that result to the outside? So that's a significant difference to all the theory, to all the physical forces so far. Anyhow, so that's the theory of all of this. And so the first real step towards hunting such objects in the universe was the discovery of the quasars by the radio astronomers in Cambridge. Those quasars then in the optical look like, in this particular case anyhow, very faint stars, but obviously very compact. Now, Martin Schmidt there on the left side used the Palomar telescope to take a spectrum, an optical spectrum of this object here, 3C273, and he found spectral lines which are all well known, hydrogen, helium, neon, and so forth, but all redshifted by 17%. So that redshift then led to a 10-year discussion amongst the theoreticians, amongst them Martin Rees and Donald Lindenbell down there. And then after that time, the consensus was that if you interpret this redshift due to the expansion of the universe, then even this relatively moderate object here is at very great distance, so that when you basically take into account that the weakening of radiation with over distance and time, well, then this is actually an object which is 1,000 times more luminous than the Milky Way. And you see actually the first other things which such sources have, namely this little crud there on the left side, which is a stream of magnetic and highly relativistic particles ejecting from the center in what we call now jets. So the picture which came about is that these are potentially very, very heftily accreting black holes, where, of course, you cannot look inside the event horizon, but when the material moves in this central region, it loses potential energy in terms of radiation, and that can be extremely efficient relative to any other source of energy. So for a black hole of Schwarzschild type, about 6% near the event horizon, and that's incredible in terms of how much you get. If it's a rotating black hole, it can be as much as 42%. So that's the model. But if you now want to go beyond and actually do the find any observational evidence, well, then of course these objects, these quasars, are so far away that at least in the late 60s and early 70s, there was absolutely no hope to try to make any kind of a measurement of the kinematics of the gas around the black hole, etc. Of the jet, yes, but not of the central region, where you might then measure the kinematics of the gas driven by the mass. So that required objects much closer. And again, Lynden-Bell and Rees wrote a very influential paper in 71, where they basically said, well, okay, maybe these very strongly accreting black holes are just sort of the exception, but and rare, but maybe if other galaxies, maybe all galaxies, have such a central massive black hole, well, maybe then you can go to nearby objects where they are not that spectacular in terms of light production, but maybe you can see it as well. For instance, that paper said go to the galactic center, because the galactic center is so much closer, only 27,000 light years, and that's was sort of the proposal of Lynden-Bell and Rees to go ahead. And indeed, in that way, first through looking at the motions of gas in Charlie Townsend's group in Berkeley, where I then became postdoc, and then later on the motions of stars, both in California with the Keck telescopes, using these big telescopes, and Andrea Guess's group, and then my group initially in California, but then in Munich, started going ahead and taking near-infrared radiation, which we can see from the galactic center, and look at the motions of stars. So that was sort of the program. Now these experiments we were doing were successful, but they took a lot of time. At around the same time, another group of young physicists at that time tried to detect another prediction of Einstein's theory, and that's gravitational waves. And if you have inspiraling objects, say stellar black holes, onto a big black hole, or two stellar black holes spiraling inward, then you might see these gravitational waves. And indeed, I show you right away this first picture there. I'm sure you have seen it, of the first case of such a inspiraling, stellar type black hole of masses, 10 to 20 solar masses at that time. I come back to this at the end of the talk. So that's the second technique which plays a role. And the third technique uses the capability of radio astronomy to have very high angular resolution through interferometry, and not just the telescopes near each other, but actually across the entire globe. So this Event Horizon telescope, whose who was used to look at M87 and also the galactic center to look at the so-called shadow of a black hole, became, active in data taking in 2017, first results in 2019. So by chance, three different techniques were ready to go at this problem, and they have the capability of very high resolution. Now, in the optical world, of course, that required big telescopes. And not only big telescopes as such, like the 10-meter Keck telescopes or the very large telescopes of ESO, 8 to 10 meter in diameter. You actually need to go beyond this in order to, make sure that the atmosphere does not distort your images. And it's a real problem because the coherence time of the waves in the atmosphere is only a millisecond in the infrared. It's minutes in the radio, so that's not so much of a problem. But in mid-infrared, near-infrared, and even optical, of course, it seemed almost hopeless to use in interferometry. But that's not true anymore, and you will see this in a second here. So by combining the light from several telescopes, you might then hope to get a much higher resolution. So not just 8 or 10 meter class resolution, but in the case of the VLT, of 150 meters. So that's a very exciting way to go about it. And indeed, we are there now. But the technical work which needed to build this instrument we have developed, especially Frank Eisenhower as a PI, required adaptive optics to correct the waves, but also to create stars, point sources more or less, very near the objects you're interested in, because the coherence and length on the sky is not very great. And it's very rare that you have a very bright star, which you can use for the adaptive optics very close to the object of interest. So what we have been developing, also in the US, of course, is laser guide stars. These are sodium monochromatic lasers, emitted from the telescopes, sent up into the upper atmosphere, and around 90 kilometers altitude, you generate, a laser star, basically exciting sodium, but is in the upper atmosphere due to meteoritic influx. And this looks like then like this. You basically create a laser star from the 4 telescopes. Then the waves come back, and you can use the information from the laser light to correct for the distortions of the Earth's atmosphere. Those are very complicated techniques, and initially it seemed very hopeless, actually, to get it going. But I can show you here our first image with the 4 telescopes in December of last year. So there is a very, very prominent and well-known star cluster, star formation cluster, and a tarantula nebula in the Large Magellanic Cloud. And if you look at the optical pictures known at that time, and including also the Hubble, actually, you see that there is a very bright central region. And observations show that there might be a very, very prominent central star, which, if analyzed, would be much, much more massive than what had been thought to exist in the universe, about 200 solar masses. And so that really presented an enigma which would be good to overcome. And indeed, there is the first image with our Gravity Plus instrument, and you can see with this high resolution, there's a double. So it's a double star, and you don't need to resort to the explanation of a 200 solar mass star. So that was sort of the obvious way to how to use this technique, but we really were interested to look at the galactic center. So here's the galaxy as seen from southern perspective, and you see the plane of the Milky Way here, obviously, but you also see that you cannot look far in because in the optical anyhow, dust in the interstellar medium, these blackish clouds there, prevent any optical radiation from the galactic center to reach us, even with good big telescopes. So you have to go to longer wavelengths, near-infrared wavelength, mid-infrared, and also, of course, radio in any case. It also is possible to do that in the X-rays, but the resolution, the angular resolution in the X-rays is not yet sufficiently large that could be helpful. But anyhow, with this kind of techniques, both the California group and we took 40 years of measurement. That's what it takes to make pictures every initially a year or a few months. Now it's every few days. And with the interferometry, we can actually now see very, very close to the central region of radio source Sagittarius A star, the motion of stars within a year. They move very fast. They move about 100 times as fast as the Earth around the sun, about 7 to 8,000 kilometers per second, and depending on how far they are away near the radio source. And they are typically on highly elliptical or even parabolic orbits. And so there would be an entire colloquium to be spent on this question how this star cluster came about. But here it's just an obvious tool to use the motions of the stars and orbits on solar system scales to then derive the mass distribution. And the lucky thing was that while initially most everyone would have expected that there are no bright stars very close to the black hole candidate Sagittarius star, we did immediately see such a star called S2, or Andrea calls it S02. And the two groups started measuring with various techniques, ever better and ever more precisely, the orbit. And you see it's a highly elliptical orbit. And on scales of several thousand Schwarzschild radii. So it's still far away. But at Perry, which is down below where you see the position of Sagittarius star as a circle with a dot, the star comes as close as about 1,000 Schwarzschild radii and moves there with 7,300 kilometers per second. The first detection of this motion was done in 2002, and then we measured the orbital time to be 16 years. And so in Munich, we felt, oh, wow, I mean, if we are ready in 16 years with a yet bigger resolution, we might be able to see the motion in great detail. And that's what we did. We built we told ESO we would like to build this interferometer for the telescopes, and they allowed us to do this. And by 2018, when the star returned, we could see its motion down below night by night. And we could actually derive the orbit with great precision. Also, with the Doppler motions, we could see, so we have all the coordinates excepting the z coordinate. But the z coordinate, the line of sight coordinate, you derive from the orbit fitting, basically. So you can use initially Newtonian physics, or then Einsteinian general relativity to derive the central mass, which turns out to be 4 million solar masses. We know that now to about 0.1% accuracy because of this beautiful orbit there. And we can also measure the distance to the galactic center with similar precision. So that's sort of our tool, but not just with one star, but with a whole number of stars. And from that, we can actually start testing also whether general relativity is correct, not only whether there's a central mass, but whether general relativity is. And general relativity predicts that if you have a light emitting source with a line source going close to a big mass, well, then the distant observer sees that the photons coming from the star near the star are much more reddened than they are at large radii. So that's the spectroscopic redshift, gravitational redshift. And in the case of the star S2, that's a 200 kilometers per second maximum amplitude, which reaches near the Perry approach. And so that is obviously requires general relativity and is extremely well coincident with the predictions of theory, and certainly cannot be followed by Newtonian physics. So the next relativistic motion you would like to see is that of the so-called Schwarzschild precession. That's the next biggest post-Newtonian effect you would expect if you have a central mass and another mass orbiting each other. And in Newtonian physics, if you have such a simple system, the orbiting star would always go in the same orbit. Not so in general relativity. In general relativity, there's a progression of a shift of the upper distance with orbit, and so when you measure the orbit very well, you can see these deviations. And down below, you can see after you subtract the Newtonian effect, the Newtonian part of the orbit, again, then below, you see that indeed, as predicted by general relativity in red there, there's deviations from Newtonian are clearly detected, and we see the Schwarzschild precession with very high accuracy now. And we have improved since then, and it's a puzzle actually that this is so, because if there are any other objects other than this one star, and they are in the galactic center, then they might perturb the orbit of that one star. And in fact, it was theoretically predicted that the Schwarzschild precession would not be detectable if there is a very strong cusping of the central potential. But we don't find that. I mean, that really seems that around the central object, there's very little extra material, such that this any kind of a Newtonian retrograde precession cannot be detected at this point. Now, of course, this is still at 1,000 Schwarzschild radii. So what one would like to do is come closer. And there is now two ways of doing this. One is to look at Sergei star, the radio source, itself in the near infrared, because the source is highly variable, and there are days when it flares up by factors up to 100, and other days it's faint. And when you have these flares, you can then, with the accuracy of the interferometric measurement, actually see that the centroid of the light point of Sergei star moves in clockwise direction, and by about 10 in the radial measure, by about 10 Schwarzschild radii. And so that's clearly evidence that there must be a concentrated mass. And if you interpret this as an orbital motion, well, then it's indeed 30% the speed of light and a Keplerian motion, so to speak, near a 4 million solar mass object. So clearly that is additional evidence that the central object is a compact source, which could be a black hole. There's another interesting issue here, and that is that infrared radiation we see from Sergei star is highly polarized, linearly polarized, up to 40%. And when you measure the polarization across, one of those flares as the light point moves around Sergei star, the polarization moves along with it. It's always perpendicular to the central region, and that is hard to believe, because if, as most people think, you have an accretion disk around the black hole, the magnetic field should be frozen in the plane of the accretion disk. But what you see here is very differently that the magnetic field is moving by itself with an orbital period the same as that of the orbit. And that can only be if the magnetic field is energetically more powerful than the gas and very strong magnetic fields. That's an interesting issue about this inner accretion zone in the galactic center, and as a result of the fact that the galactic center currently is accreting very little material. So the magnetic energetics coming from the black hole actually dominates the innermost region over that of the incoming accretion flow. Then finally, our radio colleagues, as I mentioned, want to do the experiment which Einstein also predicted and was in fact seen by Eddington in 2 years after the Einstein's prediction, and that's the bending of light around a black hole. Now, obviously, if you have light going directly into the central part of the black hole, it will be falling into it. But actually, also at about 2 times the event horizon or 3 times the event horizon size, the beams from a source behind the galactic center on the left side reaches you fairly close as a ring or shadow. That was already predicted in the 1970s by this paper by Luminet, and also Bardeen worked on this problem, and it's clearly one of the effects of the gravity on photons. And indeed, our colleagues from the Event Horizon team made a first significant measurement in 2017, published it in 22, and that's an important fact, not only qualitatively. You see, it looks like the prediction, but quantitatively, you can derive from the ring size of the shadow what the mass is inside. So in this case, the 52 microarcsecond size of the ring in general relativity means that this is indeed a 4 million solar mass object. So here we have 2 ways very close to the event horizon, a few times the event horizon size, where we have an idea about the mass. And it's the same mass as we derive further out from the stars. So after 40 years, we are indeed in a situation where from different techniques we can measure the mass. What we would like to, of course, also measure the spin. For that, we need to come closer to see another precession, namely the precession around the spin axis, if it exists. And for that, you need a star inside. That was hopeless until very recently. Now, with the much improved sensitivity of our interferometer, we can actually see such stars. There is one, S301. It has an orbit which is only at its center about 80 times the event horizon from the black hole, and it moves very, very quickly, and it has an orbital period of only 8 years. You can also see that the ellipticity is very substantial, about ellipticity of 0.98, probably telling us something about how the star actually came in there. Now, this then allows you to set a limit or maybe measure, depending on this, not only the Schwarzschild precession, which is easy to see. So if you make actually a plotting of the current, the available data, you see that within one orbit, we can already see the prograde precession is about 2 degrees because the star is so close to the center. But if there's any spin in the central object, then within, I would say, 10 or 15 years, we might be able to see that as a, so to speak, secondary effect. And that's sort of the challenge for us, our group, in the next decade or maybe 2. I hope I will still see it, but it's clearly doable with this star, and maybe we find still closer stars. So spin might be able to measure, and so from these measurements we now can derive the mass distribution. So let me summarize that. I obviously already told you that we are sort of looking at ever smaller scales, which on the right diagram there is the horizontal scale. So the black hole is on the left side. Initially, we were at fairly large distances of 10 to the 7 times event horizon side. And then the measurements got better and better as our equipment got better. And so we and also the Caltech group were able to measure the central stars. S2 I showed to you, this new star S301, and then also the motions of the innermost gas from the radio measurements and also the bright flares. So the quality to which this is predicted by a single point mass is rather astonishing. And what additional could be other than the central point mass, which is a horizontal in this diagram, is shown here below. It's a strong limit, and within the orbit of S2, say, it cannot be more than about 1,000 solar masses. That's remarkable, and was not expected, and will tell us a lot in the future if we are making still more measurements about how the stars actually make it in there, how long they last, how they get destroyed by collisions or by falling into the black hole, etc. But I don't have time today to look at that very nice part of the measurements. So we can say in the galactic center, we likely indeed have a 4 million solar mass black hole. If you compare this to the mass of the Milky Way bulge, this is about a few by 10 to minus 3. And if you look at nearby galaxies, you find what we now call active galactic nuclei, of which the quasars would be the most powerful variety. And if you plot the inferred motion of the ionized gas around these black holes from Doppler motions versus the mass of the galaxy, there is an approximate correlation. It's scattery, but an approximate correlation. About 0.2% of the mass appears to be in the central point source. Of course, in these more distant objects, we currently don't know whether these are black holes, unlike what I told you about the galactic center, but we use the galactic center, so to speak, as our anchor, and then interpret the data we have, the spectroscopic data, in that way. Now, how does this come about? Well, it tells you that if there's a correlation between the central mass and the galaxy mass, that the production of material or the flow of material from the intergalactic medium into the galaxy and then into the black holes are correlated. And that is actually quite a chore, because in order to fall into a black hole from a distance way outside of the galaxy, you have to remove all but 10 to minus 9 of the angular momentum. So you have to have a lot of friction, if you like, probably magnetic friction, but also collisions of clouds and so forth, which therefore remove ever more angular momentum. Then it leads to star formation, and then it can go on and also feed the black hole. And on the right diagram, you see how this can be now constructed for many, many cases as a function of time after the Big Bang. So we are on the right side of the diagram. The Big Bang is on the left side. And what it shows is that the star formation rate in galaxies increased in the past about 100 times. The Milky Way now produces 1 solar mass per year in the entire Milky Way. But, about 10 billion years ago, it was more like 50 to 100 solar mass. And it turns out that the relative abundance of quasars and the occurrence rate of quasars also increased by about 1 to 2 orders of magnitude going back to that time. And so this is this picture of coevolution which has developed over time. And the most recent wrinkle in that story through the James Webb Telescope is now showing us all of this growing already 1 billion years after the Big Bang. And that there is a stunningly active formation of black holes, etc. And of course, that is sort of the next big goal. Now, with our interferometry, we can also contribute in a major way, because if you have a black hole there in the center, this black as ellipsoid, and you have an accretion disk surrounding that, and gravity dominates all of this, then there is an ionized zone, the so-called broadline region, which is in kinematic equilibrium with the central mass. And so when you measure the motions and the size of the broadline region, then you can measure the mass of the central black hole. So far, this was only possible by measuring the Doppler motions, so the Doppler effect, and the size through reverberation, just time delays if you have variable emission. That's a reasonably good way of doing this, although not for distant quasars because it takes too long. Now with our interferometer now, we can actually use the direct measurement. So this is the famous 3C273 again, which I showed you earlier. There's a line due to hydrogen Paschen alpha recombination, which obviously has very broad wings. That's that broadline region. And down below, you see a curve, which is the fringe phase on one baseline of our interferometer across the line. And you can see that on the left side of the line, there is a negative differential phase. On the other side, there's a positive differential phase. And that means that the blue and the red side of the broadline region are not in the same space. And you can actually map out with the interferometer then what it really is. And it turns out to be a disk, which is red on one side and blue on the other, moving with about 16% speed of light. And then you can see that this rotating narrow broadline region is perpendicular to the jet in this galaxy. But that's a pretty nearby galaxy, actually. But in the meantime, our improvement in the interferometry is such that we can go to distant quasars. Here is a recent measurement of the same kind of information, a broad line. In this case, it's not Paschen alpha, but H alpha, because of the higher redshift. But you can see that the phases again show this S shape. And from that, we can determine the size and the mass of the central region. So if you plot the black hole masses obtained in this way versus the stellar masses obtained from the analysis of the light, then you see that we can now, at galaxies which were redshifts, quasars, redshifts of 2 to 4, so that's only indeed about 1 to 2 billion years after the Big Bang, measure the black hole masses. And what you see, first of all, these black hole masses are large. And second of all, both the measurements we make at high redshift and then the measurements the James Webb Telescope gets from scaling relations in yellow is above the correlation in the local universe. So that means that in this co-evolution, the black holes must have grown 5 to 10 times faster than the galaxies. And that's the riddle of black hole growth, which currently keeps everyone busy. How do you do this? Because, in fact, it's not that you just let more material accrete. If you do that, normally you would expect that you also generate radiation, and the radiation of photons has momentum, and that can push against the accreting material and basically, decrease the gravity effect. But apparently, these high redshift quasars manage to get beyond this. We will see how this goes. I mean, we hope to use these measurements in the next 10 years to go at the most distant early black holes, and in fact learn from that how they formed through very fast accretion, so-called super Eddington accretion, and from central star clusters, or, and that is a proposal by some of the colleagues in particle physics, because primordial black holes already existed shortly after the Big Bang, and then they could have collided and collapsed. We will have to see how far we can test this, but it's an incredibly active region now of research, both in physics and in astronomy. So, if you go back to the gravitational waves, then I showed you this picture of the in-spiral of two stellar black holes. Now, the LIGO, Virgo, Kagra trio of gravitational wave observatories has by now seen on the order of a few hundred of these in-spirals. And the remarkable thing is that the original expectation of stellar black holes only, so 10 to 30 solar masses, yes, that they are seen, but actually there are some black holes seen by the interferometry of 150 solar mass black holes. That is puzzling, because according to theory, at least in the current theory frame, it's not easily possible to have a supernova explode of such a massive object and then form a stable star in the center of that mass. And so we will obviously have to look at that, or if these intermediate mass black holes, as they are called, are a totally different path of evolution. So you see, everywhere we find riddles, and they are sort of parallel to each other. Here, the same thing. The question is this due to multiple mergers in dense environment, growth of accretion of not so massive stellar black holes, and then again the primordial black holes? I'm sure this field will be extremely active for the next 1 or 2 decades. In terms of testing GR, the statement from the most recent paper there from this year says, while one of the ring down analyses find values in the tails for its combined results, this may be due to catalog variance, and we find overall consistency with vacuum GR. So it seems indeed that that general relativity seems to be a reasonable prescription, and we don't need more complicated interpretations. And these more complicated interpretations, in fact, have been discussed. So, for instance, if you have heavy neutrinos, you might form balls of fermions. Likewise, if you have Higgs bosons or other heavy bosons, they might conglomerate to a compact but not black hole-like concentration, a little bigger than that. And there are many other possibilities which the theoretical community has proposed. In the present situation, we can indeed exclude the fermion balls, probably the boson stars by Occam's razor, but we cannot exclude wormholes or Grava stars and other things which are still a little bigger than a Kerr black hole. So in the next years, we will in Chile start a 40-meter telescope, the ELT. It's almost ready, and we hope to make progress spectroscopically there, close to black holes. The Event Horizon Telescope might make further improvements so that we can go inward in that way. And then finally, in hopefully 10, 15, 20 years, there will be a gravitational wave observatory in space. If we have that, then we can look at sort of the ideal experiment, a big, massive black hole and a surrounding stellar black hole spiraling inwards. That's an ideal experiment because it takes so long. And that means the last stages before it falls into the black hole can be measured with superb accuracy. And the prediction then is in that case, you could really be sure that this is a Kerr black hole with a no-hair theorem associated with it. So the future is bright. James Webb, I mentioned, then the ELT, and then hopefully also gravitational wave interferometry in space, which allows you to get to this Emery experiment in a somewhat nearby galaxy. So that's a lot of work to be done, but it's really at the forefront of both astrophysics and physics. Well, well. Thank you.
Thank you. Thank you very much. Questions for Professor Genzel? Feel free to either raise your hand or unmute yourself and ask.
They're all are in the black hole, so that's
They're gone.
they're gone. They cannot communicate to us.
Eugene.
Yes. Professor Genzel, it is a real pleasure to listen to your lecture. Thank you. I have a small comment about exotic solutions and some questions about the evolution of supermassive black holes and galaxies in general.
Okay.
First, last year, the clearest gravitational wave signal was obtained with a record signal-to-noise ratio in which the ring down was measured reliably. This ring down, together with Hawking's area theorem, requires the presence of an event horizon after the merger. Thus, we see the event horizon through gravitational waves. This seems to leave no room for bosonic stars, quark stars, or other exotic compact gravastar-like objects. Please correct me if I am mistaken.
I might have missed this, but as I said already, I expect that the ultimate measurements indeed will come through the gravitational waves. But of course, the current, as I explained, and as you know well, the current, evidence of the gravitational wave ground-based work is on relatively low mass black holes. Okay, and in a way, what I was emphasizing more was sort of the more massive or supermassive black holes. But physics-wise, that's in a way, whatever you like. So I should look at this. You said this was last year.
Yes.
But who is the first author?
You can Google it like the most the record signal to noise ratio
Okay.
gravitational wave.
Thank you.
Thank you. And I have one more question. If last year JWST once again broke a new record. It found a little red dot and spectroscopically confirmed in it the most distant broad line quasar at a redshift of about 9.2. There are too many assumptions in the paper to make a reliable estimate. And if, just for a moment, we accept these estimates, which is probably a big if, then the central black hole may amount to several tenths of % of the galaxy's stellar mass in the first half billion years of the universe. So my question is, what do you think about the direct collapse of large hydrogen clouds straight into a supermassive black hole that is into a large seed, of course, within a dark matter halo before the galaxy formation, with the galaxy then growing around the black hole?
Yeah, I know that's an obvious possibility, which actually theoretically already has been looked at a while ago, before all of these JWST possibilities. And yeah, no, I mean, it's a relativistic star, which, however, does not immediately collapse to a black hole, okay, or then directly collapses to the black hole without forming a star cluster. Possibility. Now, the little red dots, where is sort of the the current cry of everyone in astronomy. I'm sure we will try to do it as well. But they're actually fairly faint in the near infrared, although there is near infrared radiation. And the puzzling thing, as you undoubtedly have seen, is that in the rest frame optical, they're actually fairly faint. Then you have, however, the spectroscopic information of very broad lines, and so it's from the many such little red dots, which by now have been seen between redshifts of 3 and 14, by the way. I mean, this is enormous. There is not a unique consensus of what we are looking at here, okay? And some even don't imply black holes, but we'll see. I think this is, the clearly the most active region in JWST work right now. Hundreds of people have been working on that.
Many thanks for your answers, for the lecture, and for everything you do.
And let me just say that I have put a link to the event that Eugene mentioned in the chat for everybody to check out. So Elias has a question.
Yes, it's in fact, I have a comment for your last comment, which had to do with what black holes are good for. Well, as you know, theorists have been speculating about black holes for decades, and there are several interesting problems that are involving black holes. So I think thanks to people like you, these things eventually will start being tested in realistic black holes. And I think from that point of view, understanding, if you wish, the details of gravity beyond eventually the classical regime is something that it is very important. Anyway, thank you very much for your talk.
No, I fully agree with you. But this last little, fun piece, it goes along the line that I get every, I don't know, 2 months. I get an email from someone in the world I don't know, and someone says something along the lines. Professor Genzel, you are a very, very good scientist. Clearly, your brain must be, and really, you know what to do. But look, this universe stuff and black holes, who cares? I mean, if you wait, do something more useful, they will still will be there in thousands of years. So why don't you stop this nonsense and you do something useful for humanity? So in that sense, this little movie showed, actually was to demonstrate human greed. Yeah, I mean, you can't get enough until you disappear in the black hole.
Thank you.
Any other questions? Felix?
Yes, hello, Professor Genzel. Thank you very much for the very comprehensive talk covering lots of different topics. I had one question about the polarization signatures you showed in the infrared that were changing around Sagittarius A star. So I usually do more extragalactic black holes, so I'm only broadly aware of these studies on Sagittarius A star. But I also think there was a study showing with ALMA that there were loops found in the Q and Stokes-U plane. Were these consistent, or maybe were they looking at very different things?
Yeah, they knew our result. They knew our result, and they are consistent. And because it's astonishing, right? I mean, we learned in school, or some of us learned in school, that if you go into an accretion disk, it's very highly ionized, everything in a hot temperature. In such a situation, the accretion zone is fully ionized and the magnetic fields are frozen in. And so then if you add to this a rotating accretion disk, then you would expect, in fact, that the magnetic fields are in the plane of the orbit. And that means that if you have one orbit in space, the magnetic field rotation in Q and U makes 2 rotations. So the fact that we see equal periodicity in the magnetic field direction and in the orbital direction is really, a telltale sign that the magnetic field is essentially perpendicular to the orbit, and therefore cannot be frozen in. It's the magnetic field dominates in the galactic center. Now, I mean, this may be in other galaxies surely different, but
yes, I agree. It's very fascinating. Thank you very much.
Other questions? Eugene again?
Yes, may I ask one more question? On the slide, cosmic coevolution of galaxies and black holes, there was a plot showing activity over cosmic time. That was a wonderful epoch, cosmic noon, a very active time. Too many events were taking place then, the peak of AGN activity, the peak of star formation activity, and by the way, the dominance of baryons in the centers of these galaxies with falling rotation curves, as shown by you and your team. My question is, why did all of this activity and other dramatic changes occur exactly at that time? What was so special about that epoch?
as you go back in time, the m dot That is, the accretion rate from the intergalactic medium and circumgalactic medium increase. On the other hand, as you go beyond 10, 12 billion years ago, it decreases again because at that time, the collapse of the larger scales into the galaxies was not yet fully there. But then in this period, many people call cosmic noon, you had the situation that the abundance of material coming into the galaxies was so high that it immediately could cool down to molecular state. And that's the key, because if you have only ionized material and the intergalactic gas is ionized and hot, right? If you only have that, then you cannot form stars. So in order to form stars, you need to have fast cooling, and we have established through measurements of molecular lines now that in fact the abundance of the density of the gas in these high redshift galaxies at cosmic noon was 50 times as large as in modern galaxies. And so that's how you can get the star formation rates up. And then of course the next thing is the star formation will happen on scales of a few kiloparsecs, of course. But then how do you get from a few kiloparsecs down to the scale of the black hole, right? You have to remove that angular momentum. And that is possible because the high densities, of course, means that the collisional cross-sections of clouds and so forth is much higher, and therefore you can transport a lot of angular momentum in that way.
Thanks again.
And while the rest of the people are thinking of whether they have some more, may I ask something very practical? So assuming that your star is not, no lens steering precession is detected, right? So 0. How sensitive is your measurement? What kind of limit can you place on the angular momentum of our own?
Yeah. Well, look, I mean, the thing is, before we started this gravity experiment, people who were, courageous enough to look in the optical and near mid-infrared for interferometry had established, well, you can barely see stars. So we put this machine on the VLT, and immediately we gained a factor of about 1,000 in sensitivity. And since then, we have improved the last 5, 6 years. We have improved by another factor of several hundred. So that means not only do we get a higher angular resolution, but we can get down to fainter and fainter stars. And so the probability that we actually are beginning to see stars very, very close is getting higher. In fact, that star S301 is about a factor of several thousand times fainter than the star S2. The star S2 you can see with a big telescope and adaptive optics, but none of these new stars we are discovering very close. You can. So it's really a question of experimental fortitude, and you might in fact imagine where we are heading next, to a longer baseline. Okay, we want to convince ESO to let us build. I mean, that would be Frank Eisenhower, hopefully, and let us build an interferometer extension to about a baseline of more than 1 kilometer. Then we have micro arcsecond resolution. Okay, so that is maybe the dream.
Thank you. Anything else? Any other questions?
Well, thank you for having me, and
thank you very, very much.
I hope that the Zoom methodology has sort of worked a little bit.
I think we should reiterate our invitation to you to come back once the weather has cleared up, so that you can enjoy our hospitality under better skies. Thank you very, very much for this, for agreeing to give the colloquium over Zoom despite the circumstances.
Okay, very good.
Thank you, Reinhard.